Hey guys, Mr. Betts here. We've been talking a lot about how to take derivatives of functions and then how we can interpret those derivatives in the context of the graph of a function. So, what I want to do in this topic is kind of put those things together, specifically the first derivative and the second derivative, and what they're going to tell us about the graphs of the functions. So, we can get a lot of information about a function from its derivatives. So, for example, the first derivative we can first infer continuity because we know that if a function has a derivative at a point, it's also continuous at that point because differentiability implies continuity. We can also determine where a function's increasing and decreasing. So remember, where a derivative is positive, the function itself is increasing. Where a derivative is negative, the function is decreasing. And then using those increasing and decreasing intervals, we can also figure out where the function is going to have relative extrema. So where it's going to have a relative maximum or minimum based on the changes in increasing and decreasing intervals. Using the second derivative, we can directly find information about the concavity of a function. So when the second derivative is positive, the function is going to be concave up, and when the second derivative is negative, the function is going to be concave down. I also want to point out that important things that we're using from the second derivative, specifically whether the second derivative is positive or negative, we can get from the first derivative and look at where that first derivative is either increasing or decreasing. Because remember, that second derivative is the derivative of the first derivative. So what we're going to do is we're going to either look at a graph and answer questions like the ones I have on the screen here, or we might be given a function. So analytically given a function f of x equals 3x squared minus 2, and answer questions like these here. So if we're given a function and we're asked where f of x is increasing or decreasing, what we're going to do is we're going to take the derivative. Now, if we're just given the graph of a function like we have here, we just have to visually look at where the function is increasing or decreasing. So if I focus specifically on increasing, wrong tool. So if we focus strictly on increasing intervals, we're just going to have to look for where the function has positive slopes. Or on the other hand, if we're looking at decreasing, we're looking at where the function has negative slopes. If we are looking for where f has extrema, we're looking for horizontal tangents, or where the derivative changes, or the increasing, decreasing behavior changes from one to the other, then we get relative extrema. With concavity, it's a little bit more difficult to eyeball. So if we want to know where a function is concave up, it's pretty easy to say the function's concave up here. Let me use a different color so I can see this a little better. So it's pretty easy to say it's concave up here and it's concave down here. The trickier thing is to figure out exactly where it's concave up, because it is concave up or down along this interval, but it's hard to tell. But at some point along here, it changes from concave up to concave down. So that answers our last question: where does it have inflection points? Inflection points are a little bit more difficult to get from the graph of f. So hopefully if we had to answer that with a graph, we would be given a little bit more information, or we might be given, say, the first derivative. So if we're given the graph of the first derivative and we want to know where is the function itself, increasing, decreasing, extrema, concavity, all that stuff, this is actually a little bit easier. So if we want to know where f of x is increasing, now we want to know where f prime is positive. So this is pretty straightforward. F prime is actually positive everywhere except a little part right here where it's below the x-axis. So f of x is increasing everywhere except this interval right here where f prime falls below the x-axis. Where f has extrema then is going to be where f changes from increasing to decreasing, which would be here, or where f changes from decreasing to increasing, which would be here. So not when we're looking at extrema on f, we're not looking at extrema on f prime also. We're looking for where f prime crosses the x-axis. If we want to talk about concavity, this is where I said we can infer information about the second derivative from the first derivative. So if the first derivative on this interval is decreasing, then we can say that the second derivative is going to be negative. So on any interval where f prime is decreasing, then we know the function itself is going to be concave down. So on this interval, f of x will be concave down. Also on this interval, f of x will be concave down. On the other hand, anywhere that f prime is increasing, we're going to have a second derivative that's positive, and therefore f of x is going to be concave up. So if we're answering questions then about inflection points, then we're looking for where the derivative itself changes from decreasing to increasing. So an inflection point on f is going to be the same thing as a relative extrema on f prime. So this is going to be where f prime changes from decreasing to increasing. Then we're going to have an inflection point at the x coordinate that corresponds to that. We're also going to have an inflection point given there and an inflection point there. So remember that we can get information about the second derivative from the graph of the first derivative. Now, the last question here, last part, is if we are given the second derivative, how do we answer these questions? Well, unfortunately, we can't answer questions that are given by the first derivative from the second derivative. There are ways to work backwards and take a second derivative and go back to the first derivative, but we don't have enough information to get a full picture of what the first derivative is going to look like. So we can't figure out where f of x is increasing or decreasing given just the second derivative, because we don't know where f prime is going to be positive or negative. And if we can't figure out where f is increasing or decreasing, then we also can't figure out where f's going to have extrema. Now remember, we do have a second derivative test, and the second derivative test partly looks at the concavity of a function, which we can get from the second derivative, but we also need, for extrema, we need to know that the first derivative is equal to 0. And we can't get that again from this information, so this is another question we can't answer with the second derivative. If we know information about the second derivative, really the only thing we can do right now is figure out where the function's concave up and concave down, and therefore has inflection points. So again, using the positive and negative aspects of this, now where the graph crosses is going to be an inflection point, because where f double prime is positive, which is all of this area here and all of this here, the second derivative is positive, which means f is concave up. So we have a small section here where the second derivative is negative, and so that's going to be where f is concave down. So then if we want to answer questions about inflection points, that's going to be where the graph of f double prime crosses the x-axis. Just like with the first derivative, where we're going to have relative extrema is where the graph of f prime crosses the x-axis. So this was just kind of a summary of information that we can get from a function and its derivatives. And the questions that we're going to see in this topic are going to ask us questions given information about a function, its first derivative, and its second derivative.